Today, we're going to pull back the curtain on some hidden chemistry. It's the kind of stuff that's all over your home, from what's on your kitchen counter to what's in your cleaning cabinet.
So, you ever wonder what makes a lemon so sour it makes your face pucker up? But then, a simple bar of soap feels kind of slippery and, yeah, tastes pretty bitter if you accidentally get some in your mouth.
Well, believe it or not, that's the exact same science that makes your morning coffee what it is, and what makes the bleach under your sink so powerful.
Turns out, these things all belong to two big chemical families, acids and bases. And once you start looking, you see they are absolutely everywhere. I mean, think about it. The acetic acid in vinegar for your salad dressing, that's one. And the sodium hydrogen carbonate, you probably know it as baking soda, in your pantry, that's another. We rely on this stuff for countless things every single day.
Okay, so what is it that actually makes an acid and a base? Down at the molecular level?
Well, at first, the differences are all about our senses. Acids have that classic sharp, sour taste. Bases, on the other hand, are usually bitter. And that slippery feeling, that's actually the base reacting with the natural oils on your skin to make a tiny, tiny amount of soap. Pretty wild, right?
So the first real scientific crack at this came from a chemist named Svante Arrhenius. He suggested it was all about the specific ions that a substance lets loose when you dissolve it in water. Acids, he said, produced hydrogen ions, or H+, and bases produce hydroxide ions, OH-. Simple enough.
But here's the thing. The Arrhenius theory was a fantastic start, but it was, well, incomplete. It just couldn't explain why some things, like ammonia for example, act like a base, even though they don't have any hydroxide ions to give away in the first place. So that little puzzle led chemists to a much more elegant and really a more universal explanation that fixed all these problems. It's called the Bronsted-Lowry definition, and it completely reframes the whole idea. See, it's not about what ions get released, it's about a simple little molecular dance.
It boils down to this. An acid is a proton donor. A base is a proton acceptor. That's it. That's the game. And a proton is just a fancy name for a single hydrogen ion, that H+ we talked about.
So, the really crucial takeaway here is that every single time an acid and a base react, what's really going on is a fundamental handoff. It's a proton swap from one molecule to another. This was a huge shift in thinking because it focused on the core transaction, not just on what happens in water.
Okay, now this brand new rule reveals a surprise hero in our story. And it's the most common, most vital molecule of all, water. This brings up a really fascinating question, right? If acids are proton donors and bases are proton acceptors, what in the world is water doing in this chemical dance?
And the answer is just remarkable. Water can do both. It can give a proton away and act like an acid, or it can accept a proton and act like a base. This amazing dual role ability actually has a name. It's called being amphoteric. You can kind of think of water as the ultimate chemical switch hitter. It's ready to play whichever role the reaction needs. In a process called autoionization, water molecules are constantly reacting with each other. One water molecule will donate a proton to another one, and this creates a very small but incredibly important amount of something called hydronium. That's a water molecule with an extra proton and hydroxide ions. This whole process creates a super delicate balance in any glass of pure water. And that delicate balance? Well, that's the key to understanding the most famous scorecard in all of chemistry, the pH scale. It turns out, in pure water, if you multiply the amounts of those hydronium and hydroxide ions together, you always get this tiny constant number, known as Kw. It's 1.0 times 10 to the negative 14th. Always. And here's the really cool part. The math behind this constant is the secret to the pH scale. When you do a little math trick called a negative logarithm on that super tiny number, you get a much friendlier one, 14. And that is what sets the familiar 0 to 14 range of the scale we all know and love. So the pH scale is really just a simple way to measure the concentration of those hydronium ions. A low pH, say from 0 to 6, means something is acidic. A high pH from 8 to 14 means it's basic. And a pH of exactly 7, that's perfectly neutral. That's the balance point of pure water itself. So this constant proton tug of war, this swapping back and forth, it's happening all around us and inside of us. It's helping digest our food, it's keeping swimming pools clean. Which kind of leaves us with one final thought. Now that you know what to look for,
Where else are you going to spot this silent fundamental chemistry at work?